Hello guys, welcome back to EC TechNest. In this lecture we'll be discussing about module 4 of embedded systems design. So this module is all about the embedded firmware. So the first one we'll be discussing is the program instructions. So these are certain control algorithms and the configuration settings that an embedded system developer dumps into the code or program. It is an unavoidable part of the embedded system, and embedded firmware can be developed in various methods like writing high level language using embedded C or C++, using an integrated development environment or editor, compiler, linker and debugger. So embedded firmware design and development. The embedded firmware is the master brain of an embedded system, and embedded firmware imparts intelligence to an embedded system, and the product will continue serving the assigned task till the hardware breakdown occurs or a corruption in embedded firmware occurs. So designing embedded firmware requires understanding of particular embedded product's hardware. So the embedded firmware development process starts with the conversion of firmware requirement into a program model. So there are two basic approaches for design and implementation of embedded firmware. This is very important question that is asked in most of the exams. Explain the embedded firmware implementation approach. So the first one is super loop based approach and the second one is embedded operating system based approach. First we'll discuss about the super loop based approach. In super loop based firmware development, the approach is suitable for applications that are not time critical, which means the response can have a delay and where the response time is not that important. So embedded systems where missing deadlines are acceptable. So it is very similar to the conventional procedural programming where the code is executed task by task. So the tasks are executed in a never-ending loop, and the task listed on top of the program code is executed first and the task below the top are executed after completing the first task. So a typical super loop implementation will look like: first configure the common parameters and perform initialization using various hardware components such as registers and memory, and next start the first task and execute it. Similarly execute the second task and the next task, and keep executing the task until the last defined task, and then jump back to the first task and follow the same flow. So this is like something like an infinite loop. It will keep on executing until the condition is true, and when the condition becomes false it will stop. So this is the C program code for super loop, void main function, and inside that we have configurations and initialization. So here you can see while true, all the tasks will be executed till task n. And the pros and cons would be: it does not require an operating system for task scheduling and monitoring, and it is simple and straightforward design, and it also reduces memory footprint. Whereas cons would be non-real time in execution behavior, and any issues in the task execution may affect the functioning of the product. So the enhancement would be combine super loop based techniques with the interrupts, so that when interrupts occur it will stop the execution, and then a priority will be given based on the interrupts and execute the tasks which require real-time attention. Second most important one is embedded firmware design approach. So in this, the embedded operating system can be one of RTOS or GPOS. RTOS refers to real-time operating system and GPOS refers to general purpose operating system. So the embedded operating system is responsible for scheduling the execution of user tasks and also the allocation of system resources. So point of sale terminals, gaming station, tablets, PC, etc. are examples of embedded devices. Embedded Linux, Windows Mobile, QNX, VxWorks are example of real-time operating system that have embedded product development in it. And mobile phones, personal desktops, flight control systems are example of embedded devices that run on RTOS. Next, coming to the assembly language. we have high level language, that is subset of C programming, that is embedded C and embedded C++. And then we have mix of assembly and high level language, mixing high level language with assembly language and also inline assembly. So the first one is embedded firmware development languages or options, and the first one would be assembly language. So assembly language is a human readable notation of the machine language. Machine language is processor understandable language, and it's in the form of binary representation of zeros and ones, whereas an assembly language program is written for one processor or control family, will not work for the others. See, for example, when you write code for 8051 architecture, it will not work the same for 8085 or 8086. You have to modify the code based on the architecture of the microprocessor or controller that you use. And assembly language program is the process of writing processor specific machine code, and the opcode tells the processor or controller what to do, whereas operands provide the data or information. For example, the 8051 assembly instruction is move a comma hash 30, which moves the decimal value 30 to the 8051 accumulator register. Here move a is the opcode and 30 is the operand. It is a single operand, and same instruction when written in machine language will look like this. So the first 8-bit value represents the opcode move a, and the second 8-bit represents the binary value that represents the operand 30. So similar to this, when you convert from one language to another language, there will be certain changes that will be carried out. So each line of the assembly language program is split into 4 fields: label, opcode, operand, and comments. So the memory location address of a program subroutine. Label is commonly used for representing those, and so here you can see delay is the label that is given, and move R0, hash 255 is loading the register R0 with the value 255. DJNZ represents decrement R1 and loop till R1 is 0. So here this is the label that is used, called again, and then the control of the program will again move to the delay. And next is assembly language source file to hex file translation. So in source file to hex file translation, it's the assembly language to machine language conversion. So here you can see you have the source file 1, source file 2, which is using the module assembler to convert to object file, and then the object file are linked with the library files using the linker or locator, and then the absolute object file is generated. After the absolute object file is generated, it is converted into hex code or machine code using the object to hex file converter. And the advantage is efficient code memory and data memory usage, high performance, low level hardware access, code reverse engineering, and the drawbacks would be high development time, developer dependency, and non-portable. Similarly, we also have embedded firmware development languages or options for high level language. So the basic difference is there you will be using linker locator, and there you will be using the block called module assembler, whereas in the high level to source file to hex file translation will use module cross compiler. So the source file will be using module cross compiler to convert to object file, and then object file will combine with the library files using the linker or locator block, and then final object file is generated, and object file is converted to hex file. So the advantage is reduced development time, developer dependency, and portability. Drawbacks would be target images are created by compilers, may be messy. And next one is mixing of assembly language with high level language. So mixing assembly language with high level language like C or C++. So if the programmer wants to take advantage of speed and optimized code, so this process is carried out. Writing the hardware or peripheral access routine in the processor or controller, and then mixing C and assembly is a little complicated, but there is no universal return rule for this purpose, so we can get this information from the documentation of the cross compiler. Similarly, we have other conversion also. And the last one is inline assembly. Inline assembly is another technique for inserting the target processor or controller. So we have special keywords that are used to indicate the start and end of assembly instruction. The instruction would be hash pragma ASM. So, and hash pragma ENSASM. So this is the key C51 that uses the keywords pragma to indicate the block of the code that is written in the assembly language. So that's all for this lecture. We'll continue in the next lecture, further topics in the next lecture. Thank you.